All right. Question B1 says a car moving along a straight road. At time t0, the car starts to move from rest and the oil begins to drip from the engine of the car. 1 drop of oil is produced every 0.8 seconds. Oil drops are left on the road. The position of the oil drops are drawn to scale on the grid below such that 1 centimeter represents 4 meters. The grid starts at time t equals 0. So the first question says state the feature of the diagram above which indicates that initially the car is accelerating. Okay, let me just move this down just a tad. We can see initially or early on here the drops are getting further apart. The drops are being dropped at regular intervals, so if the distance between them is getting larger, that means that the speed must be increasing. If the speed is increasing, it means the car must be accelerating. But the feature of the diagram that tells us this is that the drops are getting further apart. Okay, part 2. On the grid above, draw further dots to show where the oil would have dripped if the drops had been produced from the time when the car had started to move. Okay, we kind of need to get a sense of how the speed is increasing in order to do this, in order to kind of backtrack and figure out where the drops are going to have dropped. So let's have a look at this accelerating bit. In this time, the car traveled 7 squares, right? In this time, the car traveled 9 squares. In this time here, the car traveled 11 squares. Okay, and then it looks like it's gonna sort of stop accelerating. Let's just go with those 3. If we look at that pattern, the speed looks like it's increasing by 2 squares per second. And so what we'll do is we'll just work backwards with that same pattern, and we'll go, this next dot must have been produced here. Oops. That wasn't very clear. Let me just rub that out. The next dot should be 5 squares back, which is there. So that's 5. The next one should be 3 squares back, which is there. And the next one should be here, which is 1 square back from that. So this is 3, and this is 1. So it shows 11, 9, 7, 5, 3, 1. That means that there's a uniform acceleration. Okay, so determine the distance moved by the car during the first 5.6 seconds of its motion. All right, 5.6 seconds. How many dots does that correspond to? Well, we want to figure that out. The drops are dropped at 0.8 second intervals. So if we take 5.6 seconds and we want to work out how many drops that corresponds to, there should be more drops than there are seconds. 5.6 divided by 0.8 is 7. So we should figure out what distance was moved in the first 7 drops. So if we count them, starting with our first one, and we have 1, 2, 3, 4, 5, 6, 7. So we go like this: 1, 2, 3, 4, 5, 6, 7. So we don't count the first drop because that's what we consider to be time equals 0. And so we've got, what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9 centimeters. 9.6 centimeters. So, so the first 7 drops. Oh, let me just move this up a bit. Seven drops. Sort of after the start. Span 9.6 centimeters on the diagram. Each centimeter represents 4 meters. So 1 centimeter equals 4 meters. So scale, 1 centimeter equals 4 meters. So distance is d equals 9.6 times 4, which we could probably do in our head, but I'm lazy, so I'm going to do it on the calculator. 9.6 times 4 is 38.4. Donk. Okay. Note that you could still get the marks for this. Oh, that's meters. You could still get the marks for this if you'd done the drops wrong. Just if you went by the same process whereby 5.6 corresponded to 7 drops, then you would still have got the full marks. Okay, using information from the grid above, determine for the car the final constant speed. Okay. The final constant speed, well, we can see here that each of these three has the same, covers the same distance. So it's 12 squares, or 2.4 centimeters. And the drops are dropped every, which equals 2.4 times 4, which is, what is that, 9.6, is it? So 9.6 centimeters. Sorry, 9.6 meters. What am I saying? So 9.6 meters. Okay. So, and the time obviously is 0.8 seconds there. So the final constant speed is going to be equal to, so distance is 9.6 meters, and time equals 0.8 seconds. And so V is equal to 9.6 over 0.8, oops, 0.8, which is, let's just check that out again, 9.6 over 0.8. 9.6 divided by 0.8 equals 12. Okay, equals 12 meters per second. Is that right? Let's just double check that. It's 2.4 centimeters. 2.4 times 4 is 9.6. Yep, that's right. Okay, and then the initial acceleration. Okay, so how can we work out the initial acceleration? Well, we would need to work out delta V. In fact, why don't we just use the distance? So we know that it started at rest, and we know that it accelerated uniformly at least until it got to maybe there. Okay. And we know that the time that it took to get to there was 1, 2, 3, 4, 5, 6 units of time, so 6 times 0.8. So, and the distance that it covered was 1, 2, 3, 4, 5. In fact, why don't we just do it for the first 5, because it's a nice, that ends on an actual centimeter mark. I have to do fewer calculations then. So that's 1, 2, 3, 4, 5 centimeters. So that corresponds to 20 meters, because each centimeter is 4 meters. So S is going to be 20 meters. The time is 1, 2, 3, 4, 5 dots as well, so 5 times 0.8, which is 4 seconds. So we can say after 4 seconds, car has gone from rest to some higher speed, and covered 20 meters. So we can say S equals 20, meters. U is equal to 0 because it started at rest. What else? We have T is equal to 4, and we're asked to find A. So looking at our data booklet, we have an equation involving U, T, S, and A. We have S equals ut plus half a t squared, and we have u is 0, so that cancels. So a is going to be equal to 2s over t squared, which is equal to 2 times 20 over 4 squared, which is 2 times 20 divided by 4 squared is 2.5. Okay, so that's question B1.